Okay.
Yes.
All right. I'm gonna see if I can share my screen here. Got some slides.
No, I'm looking at my rig runner right now.
You're coming through.
I'm coming through okay?
Real quick, I'd like to ask everybody to mute your Zoom. If you're not talking, please mute your Zoom so it doesn't interrupt the presentation. Thank you.
All right. I'm gonna cover let me see if I can get control of this. A number of topics having to do with DC power distribution, batteries, solar power. It's obviously these are huge topics, but I'm going to cover some of the things that people call us a lot about and ask about, and there's a lot of interest in, and hopefully you guys will be able to get some good ideas here. And I know everybody here knows about Ohm's law, but I want to just kind of have a demonstration here to kind of illustrate what some of the big problems are. Sometimes seeing the numbers will really bring it home. On the top there, I've got a 12-volt battery connected to a 6-watt light bulb. The loss is about 1% of the energy across that cable. On the bottom, I moved up to a 60-watt spotlight, and the loss increases to 7%. You can imagine what happens when you go to a 100-watt radio or a 1500-watt radio, what that loss is going to look like. So I just want everybody to see the numbers and understand the problems that we're trying to deal with here. Here's a table. On that previous diagram, I was using a 12 gauge cable. So I had that 7% power loss. If I had used an 8 gauge cable there, the loss would have only been 3%. And if I would have used the 22 gauge cable, the loss would have been 2/3 of the power being lost in the cable. And that's going to be enough to melt the cable. Where's the power go? It goes into heat, obviously. That's why the cable would melt. We've got a nice calculator on our website. Go to calculators, find cable size. And on the right-hand side there, you can see what the table looks like. If it shows up red, that means the insulation is going to melt off of your cable. But just tell it how long of a cable you want and how much current you're planning on drawing, and it'll give you the loss for your cable. And that includes both the red and the black wires. Connectors are a particular problem when you're drawing high current. I want to start in the lower right corner there. That a lot of you recognize that as an HF kind of connector. What they've done here is they're running 3 conductors for the plus and 3 conductors for the negative. And that allows them to split the current draw among the contacts. So even though the contacts may have a somewhat high resistance, by tripling it, they've reduced the overall heat that the connector is going to generate. At 5 amps, it's 0.075 watts. At 40 amps, it's about 5 watts. And the connector can probably handle that at 5 watts. And the reason I suddenly started talking about watts is you can think of watts in terms of the amount of heat that's going to be generated from the connector. Now, unlike a cable where that heat is distributed over a long length, the heat is going to be concentrated on just that connector. So you're concerned about it starting to melt the plastic. Right above it, we've got the concentric power jack that's used in a lot of DC electronics. Use that jack for 40 amps and you're going to lose 48 watts worth of energy. So that's going to melt very quickly. In the other corner, the banana jack, 40 amps, 16 watts of energy are going to be lost in that kind of a connector. The connector above that is the one that we're recommending for amateur radio use, the Anderson power pole connectors. At 40 amps, we have less than 1 watt of energy being lost in that connector. The resistance of that connector is 0.0005 ohms. So there's very little loss, and that's one of the reasons that we're recommending it for the amateur radio use where you're using a lot of current. And a few words about the Anderson power poles. The 15, 30, 45 amp connectors are completely interchangeable. It's the same housing, it's just how much metal and what the size is for the wire contacts. They're genderless, no male and female. Any power pole plugs into any power pole. It's impossible to put them in incorrectly, so you're not going to have a reverse polarity issue. You always want to crimp these. Don't solder them. The resistance of the solder is quite a bit higher than what you're going to get if you crimp. And again, at the high current, you don't want any additional resistance in there. So always crimp them and crimp them very tightly. If you crimp them, you actually get a cold weld. I know there's a lot of people that are suspicious about crimping, thinking, well, that's just kind of a tight fit around the cable. It really is a cold weld if you crimp it properly, and you're going to have a lot less power loss. These things are UV safe. You can leave them out in the sunlight, but they're not waterproof. Switches, you also have the similar problem that you have with contacts. There's a lot of resistance, and they tend to melt. It's really hard to find a good switch for use in amateur radio just because of the power. So solid state switches are the better way to go. But I've just got some pictures here and what the current ratings are on those switches. That 100 amp switch, that's what they use for chargers on electric vehicles. If you have a problem with power loss or contacts, it's really easy to find them. What you want to do is key down and transmit, and then go around with a meter across each of the contacts or each of the wires and measure the voltage drop. And I've got a diagram here, like a half volt voltage drop. That means you're losing 10 watts across that connection. So you can get a pretty good idea as to if the contact is dirty, if it's not making a good connection, if it's poorly crimped, just by looking for voltage drops. Again, you'd want to do that while you're transmitting. I'm going to talk a couple of grounding problems that I want to illustrate here for you. A lot of people have problems with grounding. I want to just cover two issues that we hear an awful lot. In this situation here, what we've got is a little weather station up on somebody's tower. And the weather station has like a phone cable coming down to a unit that sits on the wall and plugs into the wall. We also have on the same tower a coax going up to the antenna from a base station radio, a power supply. The power supply is plugged into the wall. Here's the problem. On the right side there, I'm showing the intended path is that green loop there between the power supply and the radio. That's where you want your ground to go, between the power supply and the radio. There's this unintended path, the blue wire. The power supply is going into the outlet is going to the weather station. The weather station is following that phone cable up the tower, and since it's connected to the tower, it then continues up to the coax and back down to the radio. So that radio actually has two ground paths to ground. When you transmit, it's going to try to split that current draw. Say you're drawing 20 amps between those two paths. And obviously the phone cable is just going to vaporize very quickly. Vehicle grounding, another common thing. The vehicle chassis is a great conductor. A lot of people want to go ahead and use that as their ground because it is such a great conductor, and it'll save you running one more wire to the trunk or something like that. Here we've got an amplifier in the trunk. The problem with that is when you use the vehicle chassis as one of the conductors, you're sharing that conductor with all sorts of other noise sources. The computer in the car, the ignition, the car radio, and the draw from those devices is going to be superimposed on the conductor going to the radio, and that noise is going to appear at the amplifier. Batteries. Start with the Rogani chart. This is what battery manufacturers just live for. What this chart is showing you is the vertical graph is showing you the instantaneous power that the battery has. The horizontal is showing you the energy that the battery has, and both axes are divided by the weight of the battery. So again, battery manufacturers are very conscious about the weight of the battery and how much energy you've got. That purple line is the supercapacitor. That shows you what that would look like. The blue line is the typical lead acid battery, and that yellow line is a typical lithium battery. As you move toward the right of the chart, it's considered a better battery source. You've got more energy per pound, essentially. The green mark there, that's gasoline. Again, the battery manufacturers are always comparing themselves to gasoline. I'm going to cover lead acid batteries first here. Always fuse the lead acid battery, put the fuse near the battery. If anything shorts, a screwdriver gets in there or something like that, you want the fuse to blow. It can be oversized. The 50 amp fuse, 100 amp fuse is fine. And even if it's a fixed fuse that you just solder into the wire, because you hopefully you'll never blow it. But if you do blow it, you'd rather blow the fuse than have the battery blow up. We recommend using a sealed battery, not a wet battery. I know a lot of people call us and say, well, hey, you said in your manual you shouldn't use a wet battery. What's wrong with it? The technology of the battery is just fine. It's just that they require a lot of maintenance. And if you're moving them from one place to another, there's a spill hazard. And the way amateur radio people typically will use these batteries, sealed is going to be much better than trying to move around or have in your basement or have next to your radio. Basically a hazard. Don't keep them in an airtight enclosure, but you can keep them inside in a room that's fine. They do vent a little bit of gas, but that gas will dilute in the air just fine. But don't put them in a sealed container, because if you put them in a sealed container, then that gas concentrates over time, and that will become a hazard. And then obviously try and dispose of the batteries properly. There's a lot of places that take free drop off on these lead acid batteries. This is the flooded battery I told you guys not to use. Just to give you an illustration of what it looks like. We basically have lead plates in there, and then it's filled with an acid that just floods the plates. This is a newer type of battery. This is the sealed lead acid battery. What they've done is they have these patties of acid that they squeeze between the plates. So instead of flooding the whole battery, you just have these little patties of acid. It's a lighter weight battery, and you don't have to keep filling it with acid the way you do with the flooded battery. There's no evaporation here. This is a picture of a typical starter battery. Now this is important because there's a lot of temptation to go out and buy a battery at Kmart or something like that, that you would use in an automobile. The automobile batteries, what they've done is they either drill holes in the plates, or they rough up the plates. I think what's really common now is they use kind of like a steel wool pasty solution that they fill the plates with. What they're trying to do is they're trying to increase surface area. The more surface area that you have in the battery, the more instantaneous power that you get out of the battery. You don't get more amp hours out of it, but you get more of the instantaneous power. So if you want to start your car in cold weather, having a battery that has a lot of surface area on the plates really helps. The problem with that is the more surface area you have in the plates, the higher corrosion rate you have. The batteries tend to corrode when they're run down, not when they're full up. On a car battery, the car battery spends most of its life filled up. But if you're using it like for radio use, a lot of times your batteries run down a little bit, and that will really promote corrosion. So these batteries won't last very long at all for a typical amateur radio use. And these are the starter batteries, and you want to stay away from them. This is a depth of discharge chart. This illustrates a little bit what I was just talking about. If you run your battery down to say 50% and then charge it back up again, run it down to 50%, charge it back up again. This chart shows you get what, maybe 1,200 cycles out of the battery, and then the battery's done. You go down to 80%, same kind of a thing. It looks like you're getting like 600 cycles out of that battery. But if the battery spends most of its life charged up, you only go down 10% back up to charge, down to 10%. you're going to get like 6,500 cycles out of that battery. So this shows the depth of discharge for a standard lead acid sealed battery. This is an AGM battery. The AGM batteries are lighter weight and more inexpensive. Instead of the acid patties, what they have these little envelopes of fiberglass that are infused with acid, and they slip those envelopes over the plates. Here's the depth of discharge chart. The orange line is showing you the AGM battery. The blue line is the same battery that we were looking at earlier, the sealed lead acid. On the AGM battery, you can see if you go 50% down, back up, 50% down, back up again, you're going to get like 200 cycles out of that battery at best, and then its life is gone. So the AGM batteries do not like to be discharged. That makes them more suitable for maybe a backup at a base station where you might only use it 4 times a year or something. In that case, you know, you're not going to ever hit that, say, 200 mark for the 50% discharge. This is a chart here of how a lead acid battery discharges. The red line shows the typical discharge on that battery. The green line is the 10.5 volts that the battery manufacturers rate the batteries at. So you can see that you're getting pretty much what they stamped on the side of the battery, a little bit less always on lead acid. You have to really charge the lead acid batteries exactly the way the manufacturers say to get 100% out of them. The problem is most radios want at least 11.7 volts for transmit. If you have that 11.7 volts for transmit, that's the blue line. You're only getting 66% of the life out of the battery. And if you account for just voltage drops at your station, the yellow line is probably more realistic. So you're probably going to get only 40% of your life out of that battery before the battery is no good for transmit. This is a similar chart, only what I did here is I cycled between receive and transmit. So I'm going between, I think it's 2 amps and 20 amps, 2 amps, 20 amps, 30 seconds each. And this shows how the battery discharges. Now, each time I'm transmitting, you can see the voltage drops about a volt or so. That changes this chart quite a bit. So now we're only getting, say, 35% out of the battery at the 11.7 volt range. And you're only getting 12% out of the battery if you take into account the losses in the cables and stuff like that. So this is just something you need to be aware of when you're using the lead acid battery. Even though it's stamped 80 amp hours on the side, you need to realize how much you're actually going to get out of it before the thing is not going to be good for transmit anymore. I'm going to move on to lithium batteries. Pretty much when you hear about lithium batteries, you think about them starting on fire, them overheating. Ever since lithium batteries came out, you started to hear stories about people saying, hey, my cell phone's getting really hot, had to throw it into the garbage can, that kind of a thing. We talk a lot with battery manufacturers. What they're telling us is that about, on average, 1 out of every 100,000 battery packs is going to have a thermal event. And my sense is over the last several years, they've kind of stopped trying to figure out why. It seems like the consumer market has kind of accepted that, and it's very hard for them to recreate that in the lab. It's just something that happens. Vehicles are worse. About 1 out of every 1,000 vehicles will have a thermal event, and about 1 out of 200,000 phones. It's just kind of the statistics that they've been having over the years. It's not like a good manufacturer versus a bad manufacturer. In the early days, they were blaming the chargers, cheap chargers versus more expensive chargers, or leaving the phones on the charger and so on and so forth. In the end, it has nothing to do with any of that. It's probably got to do with the little lithium metal fibers that are inside the phone, somehow penetrating the plastic between the polarities or something like that. But basically, all of the batteries do it, and it's roughly the same rate, depending on the manufacturer. What happens after the thermal event, whether it starts on fire, explodes, or just gets warm, that does have to do a bit with the manufacturing and what kind of plastics were used in the the shell of the battery and so on and so forth. But this is just something you need to be aware of. There are all sorts of chemistries of lithium batteries, and it seems like there's a new one every year. The one on the bottom of my chart here is probably the most popular. It's what you're used in a lot of the cell phones and laptops. The one on the top is the one that I would recommend for amateur radio use. And that's got the iron phosphate in it. The reason it's good is because it's, first of all, it's considered a little safer than the other technologies. And that means as far as you pound a nail into it, you know, how much it's going to explode. It's also considered very good for an instantaneous high load. So you start to draw 20 amps out of that battery instantaneously when you transmit. The iron phosphate is going to be a much better battery at dealing with that. But there are lots of technologies, and like I say, they come out with new ones every year. And I know there's one kicking around right now. It's basically iron phosphate, and they've added a little bit of magnesium in there. And those seem to be just about as good as the iron phosphates as well. But yeah, I would stick with the LifePo 4 batteries for amateur radio. Here's the depth of discharge chart for lithium batteries. The green line is the lithium battery. The blue and the orange lines are the same data I gave you earlier. Go to that 50% discharge. I'm getting 6,000 cycles out of that lithium battery, going down to 50%, back up to 100, down to 50%, back up to 100. So you can see this is one of the areas that the lithium battery really shines in. And I should also point out, since we're looking at this chart, the lithium battery you can run all the way down to 100% discharge, and it's not going to matter as much. I'm still getting 2,000 cycles out of that battery, going all the way down to 100. Temperature, the lithium battery is fussier. The blue line shows a lead acid battery across temperature. It's actually performs a little better when it's hot. And you can run it all the way down to very cold temperatures. Now the capacity decreases, but the battery is still operating. The lithium battery, on the other hand, once you go over 80 degrees, the life of the battery starts to reduce significantly. And once you go below 32 degrees, if you're charging the lithium battery, you run into a serious danger of the battery being damaged or actually exploding. So like a lot of your cell phones and stuff, they're designed so that if the outside temperature is less than 32, they won't charge the phone at all. Discharging is just as much of a concern if you discharge at a high rate. So again, if you're transmitting or something like that, where you're drawing the 20 amps from the battery, that would be a concern below 32 degrees. Here's that 30 seconds transmit, 30 seconds receive on the lithium battery. This is another place where the lithium battery really shines. Even using the yellow line, I'm getting 76% of the battery capacity out of that lithium battery. Remember, that was down around 20, I think it's 26% on the lead acid battery. So I'm getting a lot more bang for the buck. Now, I know a lot of you are going to look at the lithium batteries, look at the price and how much expensive they are. But you need to compare the amp hours here. These are amp hours that you're actually going to be able to use versus amp hours that you're paying for that you can't use. Just a couple of things about charging. This is important. The lead acid battery charge algorithm looks like this. We wait for the battery voltage to get up to a certain level. And then when we reach that level, we let the current draw drop down to a certain amount. And then on the lead acid battery, we go into a float stage where we just continue to apply a light current voltage to keep the battery maintained at 13.8 volts. The lithium batteries are different. The first stages look very similar, although they're much fussier about the voltage that they charge at. But once the battery is charged, once the current draw drops below 0.05 C, you want to stop charging the battery because otherwise it will overheat and then you run into other problems. So, and the reason that I'm pointing out the fact that these two charging algorithms are different is, in general, you shouldn't be putting a lithium battery on a lead acid charger because it can damage it. Now, there are some lithium batteries that have electronics in them that will tolerate the lead acid charger, but you have to make sure you're using a battery like that if you're going to, for example, use your automobile to charge the battery. This is a comparison of the prices. The blue line is the lead acid, yellow is the lithium. If all you're doing is receive only, the lithium's quite a bit more expensive. But if you're talking FM and you spend half of your time talking, the dollars per amp hour are much closer between the lithium and the lead acid. There's a chart on the West Mountain Radio website, again, under the calculator section. This looks a little bit complicated. Let me see if I can cover this. We're talking here, what I circled was somebody who spends 70% of their time talking, and the green line is CW, sorry, 70% of their time keying. You run over to the number of hours that you're looking for. Say you're looking for a 6-hour use out of your battery, and then go down. A 79 amp hour lead acid battery will last about 6 hours if you're doing CW 70% of the time transmitting. Anyway, this chart is on our website, and you can tell it to use different size batteries, lithium or lead acid, whatever you're interested in. And this will help you size your battery a little bit as to what kind of battery would be best for you. Amp hours per pound. This is the other place where lithium shines. We're getting like 6 amp hours per pound of battery versus something around less than 1.5 per pound for a standard lead acid battery. Talk a little bit about battery boosting. This is a new product that West Mountain Radio has. Basically what it does is it boosts up the voltage of the battery regardless of what the voltage is to what's going to be suitable for your transmit. We talked earlier about how you want at least 11.7 volts for transmit. If the battery's at 11 volts, this thing will bring it up to whatever you want it to be, the 12.5, 13, whatever the radio needs. So this booster can actually get more amp hours out of the battery. It's one of the options that you have versus just allowing the battery to run down like I showed you earlier. Just a price comparison here. 74 amp hour lead acid battery, $300. A 40 amp hour LiPo battery is $360. Both of those will get you 10 hours of transmit time. If you get that same 74 amp hour lead acid battery, add a booster to it, you get about 15 hours of transmit time. The booster costs an additional about roughly $250 in addition to your $300 for the battery. But if you got a 60 amp hour LiPo battery, you're going to pay $570 for that battery and get the same 15 hours of use out of it. So these are good. I know you guys are YouTubing this, so you can go through the charts later and look at all the numbers and stuff like that. I'm just trying to give you an idea of the booster's not such a bad idea if you want to stick with the lead acid battery. Because remember that that $250, you can reuse that on the next battery as well. Just a quick note here. A lot of people are familiar with the N8XJK booster. Dan originally designed it and wrote a QST article about it. TJ Electronics, from that article, started manufacturing that device because there's so much of a demand for it. Tim passed away a couple of years ago, and we worked out a deal with Dan to redesign the unit to make it more producible for West Mountain Radio. Added some additional features, and we've been manufacturing it now, I think, for about a year. Battery testing. The batteries last 2 to 10 years. 2/3 of the batteries die by the age of 7. We're talking about lead acid batteries here. Expect 5 good years at 77 degrees, 3 years at 90. So you can see where the heat makes a difference. So the guy who's got a battery sitting, outside his garage or something like that down south, he's going to have much more of a problem with life on that battery than the guy who's keeping it in his basement. Typically, when the battery capacity has dropped about 20%, then you've probably exhausted 85% of the battery. That's when we tell people to get a new battery, because it's a matter of months before that thing's going to quickly drop off. Now it's going to go from 20 to 50 very quickly. These are the things that kill a battery. This is a lead acid battery. The biggest thing is corrosion. We talked about that earlier. The main reason that the batteries corrode is when they're not charged. If they're fully charged, they tend not to corrode as much. That's why in a lead acid battery, you want a trickle charge or a maintenance charge as much as possible. Keeping that battery charged up will substantially reduce the corrosion on the battery. Dry out, we talked about the venting of the battery, how it vents some acid. Eventually too much of that acid gets vented and there's not enough acid for the battery to be effective. Those are the two biggest reasons that the batteries will die. I think I just described this slide. There's two popular methods of testing the battery. One is what you do is you put a load under the battery and you see how much the battery drops. Essentially, you're measuring the resistance of the battery. About 60% of the lead acid batteries, you can tell that the battery is about to die, or it's within its last 15% of the life. But it's not 100%. In ours, it's not a true picture of what's going on. The true capacity test, in that case, you drain the battery all the way down, measure how much energy was in it, and usually that can tell you about 95% of the time or better whether the lead acid battery is dying or not. It'll always tell you exactly where you're at as far as capacity goes. But as far as predicting the end of life, it's pretty good as well. Here are some percentages. Again, true capacity versus voltage under load. Voltage under load is what they do when you drive into the service station and ask them to check your battery. True capacity, West Mountain Radio has a device which will just essentially drain down the battery and tell you how much energy was in it. That device is called the CBA. It's really kind of fun, especially if you're at all interested in batteries. This thing can test anything from laptop batteries to car batteries, and basically just tell you what the true number of amp hours are in the battery. And it'll plot things, and you put plots on top of other plots to see how the battery is doing over life. A lot of those charts that you saw in the earlier slides were created from the CBA battery tester. And we are, by the way, we're just now redoing the software on that. It's going to have a much fresher look in about a month. This is the multiple tests on the same screen that we talked about earlier. You can do duty cycle testing like we talked about earlier. We're 30 seconds on, 30 seconds off at different loads. A bunch of the CBAs are rated based on how many watts they can discharge at a time, because you imagine we're taking the energy out of the battery, we're turning it into heat. So the standard unit that most people buy is that 150 watt unit, because that covers most of what we need to do. But they go all the way up. I think we've sold 8,000 watt systems. One cool thing that the CBA does, some of you may have applications for, we have another product called Powercheck, which is just an amp meter, voltmeter. It has an internal log. If you log the current draw from some application, say a drone or something, where you're going to measure what the current draw is during takeoff and then during landing and while it's in the air, you can take that profile, put it into a CSV file where you've got a chart of what the current draw was at each second in time. And the CBA has the ability to play back that profile on a particular battery. So you can do exactly that same discharge as flying, for example, right on the bench. So you then have the opportunity to try different batteries and say which batteries work better for the particular application that I'm going to be using. Anyway, CBA is a lot of fun. So if you're doing anything battery-wise, that might be a nice tool to pick up. A little bit about uninterruptible power supplies. The PG40S very, very popular. Many of you probably already have it. It's been out for years, one of the Westmont Radius more popular products. This is just a functional diagram here. Essentially, both the power supply and the battery feed your radio with diodes, so the battery's not going to run the power supply or vice versa. And then if you have power, AC power, there's a smart battery charger in there to keep that battery charged. When you lose power, you don't even see a flicker on the radio. It just switches right over for you. One of the common questions we have is, what about multiple batteries? If the battery is the same age and the same type, it's okay to connect them in parallel. You may want to periodically remove one of those jumpers and just put a current meter in there instead, and just make sure that there's not too much current flowing from one battery to the other. The one thing that we're concerned about in this kind of a situation is you have a bad battery, and a good battery is spending its whole life trying to charge that bad battery, and that's generating a lot of extra heat that shouldn't be generating, not to mention the energy loss. But in general, if the batteries are the same age, the same type, they're going to work together just fine. Solar power, also very hot. Here's some numbers here just to give you an idea. A 100-watt solar panel, 43 inches by 36 inches is pretty typical. On Amazon, I'm seeing about $1 a watt for a plain panel. It can go up to about $2 a watt if it's fancy. You know, you have a stand and a shelf order, a carrying case or whatever. This is another chart that was generated from our CBA. What it did is a sweep on a solar panel. In other words, it started at 0 amps and it slowly went up to 1 amp and all the way up to 5 amps. And then it showed you how many watts it was able to draw out of the solar panel based on what current it was drawing from it. The solar panels seem to have a sweet spot. This one looks like somewhere around 4 amps is where you get the maximum wattage out. So it's not a constant kind of a thing like you would expect, where the more current draw is, the less watts, or that the watts be steady. So solar panels have a sweet spot. And while I'm here, this is actually 2 charts. If you'll notice, the one that I showed you earlier, and if you look very carefully in the lower left corner, there's another plot. I superimposed that on there. This is the same solar panel. One of them is pointed at the sun, and then one is pointed at the northern sky, which is plenty bright, but not the sun. So it's important when you're using solar panels that you are pointed at the sun, and I should also point out the sun moves. With the PG40S that we were talking about earlier, you can connect a solar panel to a charge controller to the battery, and that can be in parallel with PG40S. In general, it's okay to connect battery chargers in parallel. The MPPT there, that's the type of solar charger that you would want to use on a solar panel, because what it does is it finds that sweet spot that we talked about earlier, and that's the current that it draws from the solar panel, and then it'll convert that current to whatever voltage it needs to charge the battery. So it tries to find the sweet spot on the solar panel, so you get a maximum amount of energy out of the solar panel. But again, it's okay to connect chargers, charge controllers in parallel with other chargers. We have a new product, the Epic Powergate, to replace the PG40S. The Epic has a charge controller built in, and it is an MPPT type controller. So you can connect it directly to a solar panel in addition to the power supply source and the battery source. Other than that, it's similar to the PG40S, except that although I've got diodes shown here, we're using FETs inside for the switching, and the FETs have a much lower voltage drop. If you guys remember what the PG40S looked like, it was a giant heat sink is what it looks like. This thing generates very little heat because it's got very little voltage drop. PG40S, just a standard diode, you're going to get about 1/3 of a volt drop across the diode. Here we're getting like 0.01 volt drops typically. That is my presentation. Do we have any questions?
Hey, Mark, I had a
Holy
question.
cow, thank you.
So, Mark, you were talking about the design of starter batteries, and where it is basically not really a good option. But what about deep cycle batteries? How is deep cycle batteries different from starter batteries? And because they say that they can hold a charge longer and such as that, do you have anything on that?
Yeah, that if you were to put the batteries into two big categories, it would be deep cycle and starter. So the deep cycle is what you want. You just have to be a little bit careful because the deep cycle batteries seem to be so popular when they put that on the side of the battery. There are batteries that are labeled deep cycle that aren't really. Um, what you want to what you want is the type of a battery that you would use, for example, on a boat trolling motor, because you're going to run that thing down, charge it up, run it down, charge it up. So if the advertising on the battery is talking about how many cold cranking amps it has and how it's going to start your car in cold weather, it's probably not really a deep cycle battery. If they're talking about how this is for marine use, how this is for trolling motor use, that's the kind of battery that you want.
Hey, Mark, jump in here real quick. You talked a little bit about charging batteries at different temperatures. What about just storing batteries at different temperatures? I have a very expensive lithium ion on my camper, and we're getting these down to 0 temperatures coming through here. Do I need to bring it in?
They say no, they can last just fine in the colder temperatures, but what they want you to do is to keep the battery at roughly the 40% charged rate, which I know is kind of hard. If it's a long-term storage thing, you're going to keep it out in the garage for a while, or if you're shipping it to somebody, they say to drain it down to about the 40% level, and that's the safest place for it to be sitting for storage.
Okay, thank you.
And I'll ask one, there's so many different types of solar cells out these days. What do you advise as far as a good solar cell for the house, the type that they're putting out that would keep the batteries in good shape?
It's a hard question to ask because it changes so often. There are two basic types, but really for the kind of use that we're using and the power that we're using, you're not going to see much of a difference. We're not going to compare how good a 3-inch by 3-inch panel is from one technology to another, because you guys are all going to use stuff that's multiple feet. I really think the best is to just search around and look for a good deal, because it seems like every time I do a search, it's a different manufacturer, a different type that's got a good deal. If you're using it with our Epic Powergate, one thing to remember is we've got the charge controller built in. A lot of the panels have a charge controller on the back. You don't need that. Size-wise, I typically recommend something in the 100 to 150 watt range. Some people say, well, I've got these 6 panels that comes out to 600 watts. Should I go ahead and use them or whatever? If you have more panels, that means you're going to get more energy with less light. So there's no harm in doing that. Yeah, typically about 100 to 150 watts is a good size. 150 watts seems to be very popular. But I would look a little bit too at how the thing mounts and what kind of mounting stuff it comes with. The lithium batteries, the Bioenno's got a very popular one that's being used in the amateur radio world. I know Bioenno also sells solar panels that are sort of in a suitcase. A lot of people have said that's really nice. They're probably a little bit on the overpriced side, but like I say, that's very convenient and it's a good company to be buying from.
A follow-up to that also is the number of batteries. Is there a good number of batteries to have as far as a battery bank is concerned?
It's really going to come down to what you need amp hour wise. Like I say, if you are going to have a large battery bank, you should always, periodically just measure the current draw to make sure there's not a bad battery in the bunch. So that's a little bit of maintenance concern. But it really comes down to how many amp hours you use. And again, we have that calculator on our website, so you can figure out, if you say, what I need to do is I need to survive a 48-hour power fail or whatever, and this is the way I use my equipment, just figure out the amp hours from there.
I have a question about the lithium ions, the form factor. When building a battery bank out of lithium, would you use a automotive form factor, a golf cart form factor, a remote control car form factor? What would be the best form factor to buy lithium in to build a battery bank?
The lithium is going to be a lot smaller. We build these battery boxes up of one of the products that West Mountain Radio does. And we use a standard car battery container for the car batteries. For lithium, we get a ammo container, which is considerably smaller, got a nice handle on it. They're rugged, and we use those for the lithium batteries. So yeah, it's going to be a lot smaller. So you're not going to be seeing your typical car battery kind of stuff, and it's going to be a lot lighter too as far as carrying it around. I know we built a battery box here. I'm sorry, a Go box recently, and it's sometimes hard to find the off-the-shelf lithium batteries in exactly the form factor that you need, because you might have a shallow place. You might want something that's really long and shallow. There are guys who are actually putting together these lithium batteries custom made to whatever you want. So if you want something that's more pancake shaped than a rectangle or a square cube, there are people out there that'll do that for you.
Well, these electric scooters and electric remote control cars, they have 3C, right, which I guess stands for 3-cell, and 6C batteries. Is it better to buy a lot of those smaller ones and gang them together, or would you go with the largest lithium you could get?
I'm very skeptical about connecting lithiums together unless they come that way. The reason is a lot of the lithium batteries have electronics in them so that they're charged properly and discharged safely. And it's not clear to me that electronics works well together with another battery. So for example, if I bought 2 bioenno batteries and connected them in parallel, I'm not confident that the electronics is going to work properly in that kind of a situation than just using the battery by itself. So I would stick with an entire battery that was made by the manufacturer together rather than trying to put them in parallel. The C marking on the batteries, like the 3C or the 6C, they may be referring to the maximum discharge rate on the battery. So if I have a 20 amp hour battery and it's labeled 1C, that means I can at most draw 20 amps at a time out of the battery. If it says 3C, that means I can draw 60 amps at a time out of the battery.
I see. Thank you.
Have you looked at any of the enhanced flooded batteries yet?
I'm sorry, could you speak just a little louder?
I said, have you looked at any of the enhanced flooded batteries yet?
Enhanced what technology?
Enhanced flooded. So lead acid.
Oh, we have not. No, we have customers who study those by them for the CBA stuff, but no, I don't have any experience with that.
Mark, do you have any buck converters? We've got a project working that would involve, let's say, a tethered drone. And to your very first couple of slides, that IR loss stuff is what the concern is. Anything that you have that or have seen that would take a voltage and up that voltage to maybe 200 volts DC to get up the line for a 100 or 200 foot run of tethered cable. At some point, carrying 1/0 cable gets to be tough to get rid of those losses, and when you got to drop it back down to 48 or so when you're up at the top. Is there anything that you think of that that could make that a better trip up the wire?
So you're looking at boosting the voltage up to account for the voltage loss in the cable?
Yeah, to try and get that, reduce some of those IR losses, instead of running the 40 volts or so that the drone will need. Is there anything you can think of that you could say put a 200 volt signal up, and then a buck converter or something like 20 amps is the game on those things?
20 amps. Yeah.
Yeah. Okay, you get it.
No, I'm sorry. Don't have a good solution for you on that one.
Okay.
But it sounds like a fun project.
If you want to get involved, I will say else. I think I saw Nathan, who's heading that project, on the list here. So, yeah, it looks to be an issue. Is how do you get power up there without your first 3 slides nailed right? Our problem right on the head with the IR.
Yeah. If people don't notice it, I mean, everybody knows Ohm's law. You don't notice it at the low currents, but
Yeah.
it really makes a difference when you start to talk about serious current.
Yep.
Should also point out, Orlando is trying to do a virtual ham fest this weekend. We've got a booth set up on our website, westmountainradio.com/show. And through Tuesday, there are a bunch of discounts on a lot of our products. So if you guys want to go visit the show site and get some of those discounts, there's a code on the web page and so on and so forth. So that's a good deal for anybody who's interested in buying anything.
Very good. Yeah, it looks like a good show. Starting up here about 11 o'clock, I think, our time. But they've got some good stuff signed up.
Oh yeah, good prices. And nice diagrams that show you all the pieces you need.
Yeah, we're trying to accommodate the fact that we're not driving around to shows anymore.
Yeah.
So we tried to do up a nice web page. We'll use that at all the various virtual shows.
We should get you to come for our virtual show. And when are we doing that, Mark?
Later in the year, July-ish. And we've talked to them in the past. They were planning to come out for 2020, but that didn't happen.
Well,
That didn't happen.
Oh, look at those diamonds.
You're hyperventilating, Peter.
Well, I'm just. It's if you go to the website that's on the thing there. There is a whole series, if you scroll down, of basically diagrams of all the bits and pieces you need. And of course, you can click on things and buy them because that's the point. But it's also very handy to be able to see it all laid out like that. So thank you, West Mountain Radio.
Okay, on behalf of the club, I'd like to thank Mark for joining us today. It's been pretty educational. We appreciate you taking time out to enlighten us on this. We thank you a lot. With that, I'll turn it back over to Galen.
Thank you for inviting me.
Hey.
Yeah, thanks a lot.
Thank you.
Man.
Mark, thank you for being here today. We certainly appreciate it.